Alright, hi guys. This video is actually a revision. It's a revision for chemical bonding itself. So basically, you should have received this set of notes from Mr. Tang. Okay, so these notes that we are starting off first, right, is on ionic bonding. Take a quick check to make sure that ionic bonding notes, right, as what you are seeing over here, as well as at the back of the notes, right, there should be this piece of assignment at the end. It's 4 pages long. Okay, there's some dot and cross diagrams, so on and so forth. Okay, so this is what we'll be using for this particular session. Okay, at the end, you do need to submit your work in. Okay, so the work is the 4 pieces of assignment that I showed you just now. So as I bring you through this set of notes, right, just make sure you also copy down some of the important details as we revise for this part on ionic bonding. Okay, so first and foremost, right, just a quick recap. Why do atoms actually form ions, and what exactly is the meaning of a noble gas configuration? Alright, the atoms of noble gases, right, are what I call chemically stable atoms. So what is the meaning of being chemically stable? If you take a look at their electron configuration, right, you'll realize that it's actually fully filled. That means the valence shell, right, the outermost electron shell, has a completely filled electrons. So basically, this means that they have a completely filled outermost shell. Okay, sometimes we also say that because they have a stable electronic structure. So the meaning of stable electronic structure means that they have a completely filled outermost electron shell. Okay, so let's get this right first. So basically, all noble gases are like that. Okay, so if you take a look at this part of your notes, right, basically for helium, the electronic configuration is 2. Number of valence electron is 2. Okay, the outermost electron shell, the valence shell, okay, valence means outermost. Because it only has one shell, right, this shell itself can only hold 2. So basically, they are reaching the maximum already. This is what I call a duplet configuration. Okay, you don't need to worry too much about this term itself. For neon, right, you realize it's 2.8. Okay, the number of valence electrons is 8. Because you're looking at the second shell, right? Second shell maximum is 8 electrons also. So this is what I call an octet configuration. Okay, octet because there's 8 electrons on the outermost shell. So basically, these two are just examples of why noble gases are stable electronic structures. Okay, but if you compare to other elements, right, the atoms of other elements, okay, they're actually reactive. Or basically, they are unstable. Reason being, they do not have a stable electronic structure. So this is the reason why in this part of the revision, right, we'll be talking about how ions are actually formed. Because once there's no stable electronic structure, right, every single thing in the world, right, wants to get a stable electronic structure. So what they will do is they will actually go and react. And they might react by doing one of the following. Number 1, they can either gain or lose electrons, which is the focus for this topic. Okay, and this will form ions. Number 2, they can share. Okay, if they share electrons, that's what I call covalent bonding. So take note, in this topic of chemical bonding, right, there's 2 different kinds that you need to take note of. One is ionic, one is covalent. And of course, the easier way to remember how to take note of which one is ionic, which one is covalent, you can use a shortcut, which means that you look at the elements, right, if it's between metals and non-metals, right, likelihood is going to be ionic bonding. If it's between non-metal elements only, likelihood is going to be covalent bonding. But you do need to take note, for ionic bonding, right, sometimes it's not always metals and non-metals. We'll talk about this later on. Okay, so bring you through this set of the notes, page 2, how are ionic compounds actually formed. So basically, ions means particles that are actually charged. So you're either looking at positive or negatively charged structures. Okay, and to do that is either by gaining or losing of electrons. Okay, so that you ensure that at the end you can get this thing called a stable electronic structure. So basically, every atom, right, if they are not stable, they want to become stable. And to become stable, right, they can choose to either form ions depending on what they're reacting with, or they might form covalent structures. Okay, so whenever you are losing electrons, you form positive ions. Now, electrons are negative. This means that if you lose something that's negative in your life, right, you become more positive as a person, right? So this means that you form a more positively charged ion. Okay, for every 1 electron that you lose, right, you get 1 plus charge. For 2 electrons you lose, you get 2 plus, so and so forth. So most of the time is the metallic elements that will lose electrons. Okay, usually metals will lose electrons to form cations if they are reacting. Okay, I repeat, if they are reacting. So for instance, the sodium biotite, if you look at the periodic table, it has 11 protons. So biotite, it should have 11 electrons. That means the electron configuration should be 2.8.1. This part is not stable because the third shell should have 8 to become a completely filled one. So there's 2 possibilities that can happen. Number 1, either get this sodium to go and add 7 more, then you get 2.8 by 8, or you just lose this one and you revert to your 2.8 instead of going to 2.8.8. Okay, the answer is that it's easier for the sodium, or more likely for sodium, to actually lose one electron. Then it becomes 2.8. Okay, when you lose that one electron, now this is the losing part. That's why this one will become a positive ion because electrons are negative. Okay, so when you have less electrons, in this case, it actually become more positive. So how does it look like in a dot and cross diagram? This is how I will draw the structure of a sodium atom. Okay, this is sodium atom. Okay, of course in the middle you just write Na. Okay, so you have the electrons being drawn out, 2.8.1. This is the valence electron, the one that's outermost. If it reacts, right, if sodium reacts, you lose this electron and you end up with just 2 shells and you end up with a plus charge. This plus charge here is because you lost one electron. Okay, how do you explain this in words? Because drawing it out, right, is quite clear cut. You can draw it out the entire diagram. But if you want to explain it, right, you have to show that you understand what's going on. Do mention at the start what is the original sodium's electronic structure. To show that you understand that if I want to become stable, right, to get this stable electronic structure of 2.8, I need to lose away this one. Okay, so you make the emphasis on this by using the electronic structure to explain your answer. Because sometimes, right, you need to write out why will this thing form this positive ion. So you need to explain, oh, because at the start it was like that, therefore you need to lose one valence electron to form a stable electron structure. In the opposite manner, for anions, right, anions, because they are negative ions, it means that they must gain electrons. So when they gain electron, okay, so when they gain electron, right, because electrons are negative, right, so when you gain something negative, you become negative, okay, so you become more negatively charged. If you gain 1, you become -1. If you gain 2, you become -2, so on and so forth. So most of the time, it's non-metals. Okay, most of the time, it's non-metals, they'll gain electrons to form anions. Okay, so this is just an example again. Basically, this one is for chlorine atom. Okay, inside we'll just write chlorine. Okay, so chlorine atom by itself, you look at the periodic table, right, is supposed to have 17 protons, by right. And if you recall the previous chapter in atomic structure, right, 17 protons means you should have 17 electrons, okay, in the electronic configuration of the atom. Which means that if you write it out in terms of the electronic structure, right, it will be 2.8.7. Now, because it's a 0.7 at the end, it's not stable. It's not a stable electron structure. So either you gain 1 more or you lose this 7. And the easier way is to gain 1 more. Okay, when you gain 1 more, the electron will go in. And this time around, this electron, right, help me change in your notes. It should be a cross over here. Okay, we don't use back the same symbol because it's very, very hard to tell which electron came from which atom. And you end up with a bracket and a minus charge. How do you explain this in words? You will say, what is the original structure of the chlorine atom? Because it's 2.8.7, right? So it's not stable. If it's not stable, what must I do? Emphasize that you need to gain 1 more. Okay? Once you gain 1 more, then it becomes a stable electron structure. So that's how you explain the entire thing. So that's for the formation of these ions. Now, if you have something forming cation and something forming anion, together this entire set, right, can form what I call an ionic compound. Okay, an ionic compound actually looks like this. This is what I call an ionic lattice structure. Okay, so this is a structure that looks like a Lego block. It's made out of many different things stacked together. And each of these things, if you look closely, right, there's actually a lot of ions. So these smaller blue circles here are represented by the sodium. It's representing the sodium ions. The green one is representing the chloride ions. So this entire compound, right, is sodium chloride. Okay, so inside sodium chloride, there must be sodium ion, there must be chloride ions. Okay, and this is how they are arranged inside the entire structure, looking like this lattice structure. Okay, so that's just to give you an idea of what's going on. So how do we draw ionic compound? We cannot expect you all to draw out this entire thing. Okay, because it's too much work. You can't really draw out the entire configuration of what's going on. So we usually ask students to draw a dot and cross diagram. So what is a dot and cross diagram? A dot and cross diagram, right? Basically, we're asking you to show us how will the compounds, ions actually behave and look like. So what I have over here, okay, is your dot and cross diagram for sodium chloride. You realize it's just a combination of sodium ion and chloride ions, right? The reason why it's drawn 1 by 1 because this is a plus charge and this is a minus charge. Okay, that's why the formula is NaCl, because it's 1:1. Okay, that's why you only draw 1, 1 side by side. Okay, but if the formula is different, right, that means you must draw differently. Okay, do take note also that how we actually intentionally use a cross to represent the additional electron, because from sodium, right, all the electrons initially were crosses. Okay, but for chlorine initially were all dots. So you need to be able to know that the new electrons that come in must be represented by cross. how do you show the chemical formula? Okay, in order to show the chemical formula, okay, you must know what's the charge of the ions. Okay, this is something that I call valency. So valency allows you to know what's the charge of the ion. So basically, I'm just going to run through this very, very quickly because we have been doing this quite a bit already. So for certain of the ions, right, you do need to remember, and actually you need to memorize what are they representing. Okay, so I'll give you some guide on what are those that you need to memorize. Okay, number one, you know that zinc ion, right, and silver ion, those that I'm highlighting now, has a fixed charge. So I'm going to explain how do you know what's the charge later on. Number two, you need to remember that all these polyatomic ions, okay, they also have a fixed charge, and you need to know what's their charge also. So you need to know the formula by heart, okay, so that you don't confuse yourself as you go along, because chemical equation will tap on a lot on this thing. So for hydrogen ion, right, the first thing, because the cation is has a +1 valency, it means that when we write out the formula, we write as H+. The sodium, we write as sodium plus, K plus, so on and so forth. So if you look at the charge over here, you can deduce what's the formula over here. So you can do this by yourself. The only one that I'm going to give you a hint on is silver. Silver as an ion is Ag+. Okay, this is something that you need to remember. Zinc as an ion is Zinc 2+. Now you do recognize that I'm talking about ions. Okay, if you are asking about what is zinc metal, okay, just the metal itself. Zinc metal itself is just Zn. Okay, no 2+ because it's just a metal. But if you are talking about zinc ion, like over here, it's Zn2+. Okay, likewise for the rest of them that you see over here. Now all these numbers that you see over here, right, because you learned oxidation states already, these are actually representing the charge, okay, or the oxidation state. So if I write chromium 3, it means it's Cr3+. And now you're learning cations QA. So iron 3+ will be Fe3+, and 2+ will be Fe2+, and so forth. Okay, you can do the same thing for the anions over here, but just take note that now it's all negative charge. Alright, moving on to the polyatomic ions. Now this set of polyatomic ions, right, are very, very crucial because you'll be seeing them a lot, be it in terms of the salt preparation or other kind of reactions. So it's required for you to know how exactly are the formula like. So basically there's only one, right, that is positive, and that's ammonium. Okay, take note, ammonium is not ammonia. Okay, ammonia is a covalent compound which is NH3. Okay, ammonium is a cation, it's different. Okay, so just take note that there's a difference over here. Okay, if you look at these ions that I show you over here, the polyatomic ions, right, what makes them special is that they have 2 or more atoms, which means that you are looking at the number of atoms inside. Like for instance, for ammonium, right, it shows that there's 4 hydrogen atoms inside. Okay, and there's 1 nitrogen atom, and overall it gives you a positive charge. Okay, so together this whole set is a polyatomic ion because there's a lot of atoms inside. Okay, last over here you see all the other examples for the anions, hydroxide, nitrate, sulfate, carbonate, so on and so forth. Okay, for this one, right, it's not so important for you to remember now. Okay, you might come across it time to time, but I will emphasize that you take your time to go and remember these few: ammonium, hydroxide, nitrate, sulfate, and carbonate. Okay, so just spend some time to go and run through all this formula with you. Now, because ionic compound must have anion and cations, right? Because in ionic compound, the meaning of a compound, right, means that there must be 2 or more elements inside, and that means inside this thing must have usually a metallic and a non-metallic ion. Okay, usually, or rather to make it more specific, right, there should be a cation and an anion inside this entire ionic compound. Okay, so when you derive the formula, right, same thing, you need to have the formula for the cation, you need to have the formula for the anion. Okay, then you can combine the formula together to know what's going on. So over here, this example that I'm showing you, right, is between this thing called calcium ion, okay, and this thing called chloride ion. Now, how do you balance the entire charges and to get the formula? Okay, if you think about it for a second, right, because there's a 2+ here, right, but there's only a minus here, right, it's not balanced because there's too much of the positive already. Here got too little of negative. So how do you balance it? You balance it by, okay, mentally, you need to add in another Cl minus, and this will help to balance up the entire charge, because now with these 2 Cl minus, actually there's a 2+ over here for the calcium, and you can balance the entire thing out. Okay, so what you're doing over here, right, you're actually trying to say that for 1 calcium, there must be 2 chloride, and that's why the formula derived over here. That's one way to do it. Okay, another way to do it, which is just a shortcut, okay, basically it's called a Criss-Cross Method. So you take the 2 over here, you bring it down next to this anion. Over here in front is a 1 because there's nothing written there, so it's a 1. Read down over here, so then you have a calcium 1. Okay, but we don't write 1 in chemistry, so it's CaCl2. Okay, so this is the entire way of representing the entire thing. Okay, but I prefer the first method that I showed you all, because from there I can learn, I can understand why the charge was balanced. Okay, so sometimes some of the balancing and the entire outcome that you get, right, there'll be a bracket one. So I'm going to show you an example over here. When do you know whether you should put a bracket? For instance, let's take a look at the last one, copper 2 hydroxide. Okay, copper 2 hydroxide, inside, right, the ions are copper 2 plus and hydroxide ions. Okay, if you remember the page I showed you earlier on, you should be able to derive these two very easily. In terms of the chemical formula, right, if you use what I taught you previously, you'll know that these two charges are not balanced. That means, how do I balance it? Mentally, I need to add another OH minus. Then I will know that, oh, these together will be balancing up with the copper 2 plus. Then when I do this out, right, I will know that, okay, that means I have Cu, but I have 2 of the OH, right? If I have 2 of the OH, it means that I must put a bracket and I put OH and a 2. Okay, why? Because OH is a polyatomic ion. Okay, if it is a polyatomic ion, it means that inside this entire ion, right, together OH comes as a set. So if you're going to put a 2 outside to represent them, right, you must always put a bracket. If not, it doesn't show that it's a set. Okay, so this is something to take note of. Of course, if you want to use the Criss-Cross method that I mentioned just now also, you can also do that. So you take this 2, you bring down. You take this 1, you bring down. But the problem that I don't want you all to end up with is you write this CuOH2. Because a lot of people will just write like that because they just bring a 2 down. They don't really go and think about how come the charge was balanced. So that's why I emphasize on the need for you to balance the charges. That is more important. So to understand that you balance the charge means that I need 2 sets of the OH, so I put a bracket here. That's why I derive this entire answer. Okay, so that's for CuOH2. Okay, that's why we do in this manner. Now, some other questions that might require to do that. For instance, if you look at the one above it, ammonia and carbonate. Ammonium is NH4 plus. Carbonate is CO32 minus. Now, once again, you're looking at polyatomic ions. You're looking at very big ions. So when you want to balance up the formula, right, you need to take into account how to balance up the entire formula. Which means that you must understand that if you want to do the balancing act, there's only 1 positive charge here. There's a 2 negative charge here. How should I represent them? Should I put a bracket or I don't need to put a bracket? So you try this out for yourself. Okay. If you pause the video now, you can go and practice writing all these things out. Because in the next 5 seconds, right, I'll show you what's the expected chemical formula. Okay, now let's take a look at what are the expected chemical formula. Okay, so nothing beats getting your own practice rather than looking at the answers, because in the exams, right, no one is going to tell you the formula. So whether you write it down for now for a revision, only you'll know how much effort you put in. So try it out for yourself. Take note that sulfite is not sulfate. Okay, in case you got confused, sulfate is SO42 minus. Sulfite is S2 minus. So there's a bit of terminology you need to take note of over here. Okay, if not, we'll move on to the next page. Okay, for the next and the last page, okay, I'll just go through with you what are the physical properties for ionic compounds. Okay, so in terms of physical properties of ionic compound, take note that there's a few that is very, very important. Okay, actually A and B are the most crucial ones. So you will see how I explain it on. So first and foremost, ionic compounds, right, what makes them unique is that all of them have high melting point and boiling point. Okay, so all ionic compounds have high melting point and boiling point. Okay, which means that if you look at their data, right, you can see that it's always a large number, okay, in terms of melting and boiling point. Why? Because if you recall at the very, very start, I told you that in an ionic compound, right, they actually look like this. Right? So this is the ionic lattice structure. Inside this entire structure, right, there's a lot of ions inside. And all the ions are actually attracting the oppositely charged ions, because the positive one will attract the negative one. The negative one will also attract the positive one. So imagine this entire thing goes on for a very, very, very long scale, right? Because this lattice structure is very, very big. So you have all this attraction within itself inside entire thing. That attraction is what I call electrostatic forces of attraction. It's very, very strong. And if you want to melt or boil something, right, like what you learned in kinetic particle theory, okay, melting, right, based on your kinetic particle theory, means you go from solid to liquid. Which means that your atomic structure, right, will change from this format to something like this. Okay, the particles won't be that neatly arranged anymore, right? In order for that to happen, you need to overcome forces of attraction. Which means that if you look at it in terms of the perspective of an ionic compound, right, melting means that I mean to overcome the forces of attraction, which means it's the ionic bond. If the ionic compound, the entire structure is like that, it's going to be very, very hard to overcome all these electrostatic forces of attraction because it's very, very strong. So that's why we can conclude that most likely ionic compounds, all of them, will have high melting and boiling point, because in the lattice structure of the ionic compound, okay, there exists strong electrostatic forces of attraction. Not only are they strong, because this is actually in between all the positive and negatively charged ions, right? So this is between the oppositely charged ions. Now we need to emphasize that it's between oppositely charged ions. And in this question, we are focusing on why they will attract. So we don't want to talk about ions in general. We want to say that it's between oppositely charged ions. We can also say that it's between negative and positive ions. Because it's very strong, right? A large amount of heat is needed to overcome this attraction. Okay, and therefore they have high melting and boiling point. Now if you look at how I structure my answers, right, there's 4 different parts. I start with the first thing by talking about the structure. Then I talk about what is in between the oppositely charged ions. Is it electrostatic force of attraction or something else? Then last but not least, I ended up with what's the amount of heat needed to overcome this attraction. Then I say what is the melting and boiling point. It is what I call an acronym, so you can remember how to phrase when you're asked to explain about why does it have high melting point and boiling point. It's called SIAM. Okay, S-I-A-M. Okay, so you talk about structure first, then go and talk about what's in between the particles, then go on to what's the amount of heat, then talk about what's the melting and boiling point. Okay, so this is actually a recommended way for you to explain why does it have high melting point and boiling point. And if you revise through our 10 series, right, you realize that there's a lot of such questions in chemical bonding to ask you why. Okay. The second thing that makes ionic compounds special in terms of their physical properties, they can only conduct electricity in the molten. Okay, and when we say molten, right, it's actually the same thing as liquid, okay, or aqueous. Okay, only in these 2 states they can conduct, but not the solid state. Okay, that means if you take the ionic compound, right, you melt it or you go and dissolve it. Aqueous means that it's dissolved already, so it's a solution form. Okay, if you melt it, it becomes liquid. So basically, if you do that, right, it can conduct electricity. Okay, but if you don't do that, if it's a solid form, it cannot conduct electricity. The reason being, for things to conduct electricity, there must be what we call free moving charged particles. That means there must be something that's free moving inside for that thing to conduct electricity. So ionic compounds in a solid state, right, they cannot conduct because the ions, right, they are not able to move. Why? Because they are held in fixed position by what I call my strong electrostatic force of attraction. All these ions are there, but they are already held in the same spot. They cannot move. They can only vibrate about their fixed position. They cannot move around to allow you to conduct electricity. But when you dissolve or when you melt it, right, the ions are no longer held in fixed position, because we learned in the kinetic particle theory that in liquid state, okay, particles can slide. Right? So if you were to melt the entire substance, you are looking at the structure changing from what you have initially to something that looks like a bit like this. So the particles can actually be moving around each other as they slide across each other. So when they slide across each other, right, they can carry the charge with them. So we say that there are free moving ions. We don't use the word mobile as well. We say that there are free moving ions. That means they are able to move around. Okay, and as a result, because of that, they can conduct electricity. Okay, and last but not least, ionic compounds, they are soluble in water most of the time, but insoluble in what I call organic solvents. Okay, you'll learn more about organic solvents in the last chapter of the entire syllabus. Alright, so this is actually how we can use the ionic bond or the electrostatic force of attraction to explain the different physical properties. Okay, and this is for ionic compound itself. With that, it's time for you to go and try your own practice. Basically, everything you have over here is trying to test whether you understand what I went through just now. Okay, you have the chemical formula as you see over here. Draw all the structure. Okay, it's crucial. All this structure, right, the dot and cross. Okay, you need to draw all electrons. That means the inner shell one, right, even if there's only 2 inside, you also must draw it out. Okay, so I give you an example. Okay, let's take an example, say sodium fluoride. Okay, what you need to do to help yourself with this piece of work, right? Ask yourself, when you look at sodium fluoride, is it a compound or is it an element? So if you look at it properly, it's a compound because there's two different elements inside. So this is a compound. And if it's a compound, right, is it an ionic compound or is it a covalent compound? How do you know whether is it ionic or covalent? You can always look at the elements that's inside and ask yourself, is there a non-metal and a metal being combined together? In this case, sodium is a metal. If you look at the periodic table, you should know this. Fluorine is a non-metal. Okay, together they form an ionic compound. So we are looking at ionic compound. If it's an ionic compound, it means that I need to understand this sodium, what will be the charge? This fluoride, what will be the charge? Okay, so sodium as an atom, right, it should be 2.8.1. Fluorine as an atom is 2.7. Okay, like what I mentioned at the very start of this video, how do I know whether they will become stable or not? They must do something to themselves. So this sodium will want to lose 1 electron. This fluorine will want to gain 1 electron. Then they'll become stable. So how will that look like when I draw it out? When this sodium lose 1, right, I know that it's no longer 2.8.1. It's 2.8. So when I draw it out, right, I'll draw sodium like that. 2. And the second shell with the 8 electrons. So it will look something like this. North, south, east, west. North, south, east, west. Okay, because I lost the electron already, right? So I'm an ion now. And ions must have the bracket and the charge. So because I lose 1 electrons are negative. So if I remove something negative from my life, right, I now with a positive charge. That's my sodium. Okay, for fluorine, okay, now that I gain 1 electrons, I will no longer be 2.7, instead I will be 2.8. Okay, which means that when I draw it out, I need to show the inner electrons. This time I use dots because it's dot and cross diagram, so you must use different symbols. And try to be as neat as you can. This is quite a bad example, but try to be as neat as you can to make sure that when you submit the photo is clearer. So this is my fluorine. Initially it's 2.7, but now I gain 1 extra one, right? The extra one actually came from sodium, so I must put a cross to represent the extra one. And because an ion, I need to put a bracket. Because I gain something that's negative, right, I become more negative. And this is how you show an ionic compound. Okay? Of course, if you're asking what if there is more than 1 sodium or what if there's more than 1 fluorine, for instance, say something like sodium oxide. Okay, sodium oxide, if you go and derive the entire thing, same thing is a compound. Okay, if you think about it, same thing is an ionic structure. Okay, because there's a metal inside and there's a non-metal being combined together. Sodium by itself is 2.8.1. Oxygen by itself is 2.6. Okay, to become stable, this fella here needs to lose 1 electron. This fella here needs to gain 2 electrons. Now the reason why I'm even thinking about gaining or losing, right, is because I first know whether they are ionic compound or not. If they are covalent compound, right, which you explore in the next session, right, you totally don't need to lose or gain. You just share. Okay, then we'll explain how to do that. So if you lose 1 here, you gain 2 here, you realize that this sodium actually becomes Na+, and this oxygen actually becomes O2-. Now, you cannot just draw 1 sodium and 1 oxygen already, because you realize that this is 1 positive charge, this is 2 negative charge. Which means that this formula by right should be something like this, Na2O, because you need 2 sodium. You need 2 sodium to balance up with the charges of the oxygen. Which means that when I draw it out, okay, right, there also should be 2 sodium and 1 oxygen. When I draw the dot and cross diagram. Okay? But I cannot put a sodium side by side with each other because positive and positive will repel. So my structure will look something like this. Sodium, oxygen, sodium, something like that. Okay, then you go and fill in the entire diagram. So basically, why I put oxygen in the middle is because oxygen is a negative charge one. I don't want to put these 2 positive one together. Because if I put these 2 positive together, right, I'm showing that I don't understand that the ions must be oppositely charged. Okay, so this is how I can draw the entire thing. So I have my oxygen and my sodium, etc, etc. Okay, so try this out for yourself. Then once you're done with the work, right, take a photo using the scanner app and upload it back into this assignment. Alright, thanks.